Greetings, everybody. Let's continue our discussion of curvature now. So from the example that we went with, we saw that a circle of infinite radius would essentially just look like a line that when we zoomed out from our GeoGebra example that for all intents and purposes that thing really just looked like a line until we then zoomed out further so that we can actually see what curvature was going on there with the circle. But if we had a circle that had an infinite radius to it, it would pretty much be indistinguishable from a straight line. And so that's really the intuition for defining what we will mean by the curvature function. So the curvature function kappa of s, so that's the Greek letter kappa denoting for curvature. So kappa of s is really nothing more than the length of the derivative of the unit tangent vector with respect to arc length. And so when we just have straight lines, the idea behind our straight lines is that fundamentally we think of straight lines as not curving. And so from our circle example, if we take the limit as our radius heads off to infinity of our curvature function for the circle, then that thing really was just a 1 over r. It does head off to 0 as our radius heads off to infinity. Okay. Kind of another intuition that we have is that the circles should have a constant curvature so that no matter what happens, this thing, no matter which direction or which point we're standing on at the circle, the curvature should always be the same. And that's exactly what we find with this curvature function. And kind of the idea is that the bigger the circle, the less it looks like it curves. The smaller the circle, the bigger the curvature. And so it makes sense that it is also this kind of reciprocal relationship that we just have 1 over the radius for our circle. And so what does the curvature look like for just an arbitrary parameter? And so kind of going back to the chain rule, remember that we had our d by dt is really just ds by dt times d by ds. And so if we go back to our arc length function, we took the derivative of the arc length with respect to the parameter. It was just really the length of the tangent vector for the curve. And so if we do d gamma dt, that's really going to be ds dt, d gamma ds, and that d gamma ds was really our unit tangent vector. So we get the length of the unit tangent vector, or we get the unit tangent vector times ds dt. Well, now if we do the same thing and do the second derivative, well, that's going to end up being the derivative of the product that we have here. So we have the derivative of the arc length function, or the second derivative of arc length with respect to time, times the unit tangent vector plus the derivative of the unit tangent vector with respect to time, but that was our just ds dt dt ds. So we're applying this operator up here for our d by dt, and we have our ds dt out in front. So our second derivative of our curve looks like the second derivative of our arc length function times the unit tangent plus the square of ds dt times dt ds. Well, if we use the fact that t is just gamma prime over the norm of gamma prime, then we take the cross product of both sides, what happens? That we get the second derivative cross the first derivative, and our constant that's out here, there's just this length gets pulled to the outside. Well, if we take the cross product of the unit tangent with the unit tangent, that thing is 0, so that term totally disappears, and we get this dt ds cross t just remaining. All right, so now if we go through and take the norm of all of this, what we have is the norm of the cross product of the first derivative and the second derivative divided by the norm of the first derivative. is equal to this constant that we had there, this ds dt squared, and then the norm of our cross product of t and dt ds. Well, what is this thing? Again, going back to our vector notation, that was the length of dt ds times the length of the unit tangent times the sine of the angle in between those. Well, remember that we've kind of done this several times now, that because the unit tangent vector is constant length 1, it's going to be orthogonal to its derivative. And since it's orthogonal to its derivative, the angle is going to be pi over 2, and so that becomes 1. The unit tangent becomes 1. And what we're left with is the norm of dt ds. Well, that is our curvature function kappa. And so what we have now is that the norm of the cross product of the first derivative and the second derivative divided by the norm of the first derivative is equal to the square of the norm of the first derivative times our curvature function kappa. So if we just divide both sides by that norm, then we get an expression for our curvature in terms of an arbitrary parameterization. So we didn't really care necessarily that in this situation that we are parameterizing things with respect to arc length or not. That doesn't matter. We just chose an arbitrary one. And so this is the expression that we get for the curvature. Now, if we look at the special case of just if we have y as a function of x, then what we can do, we can just take the parameterization of gamma t being t and x being t and y being f of t. Well, we take the derivative, so we get 1 f prime. We take the second derivative, we get 0 f double prime. And basically, we just kind of plug into that formula. So we take our cross product of the first derivative and second derivative, end up with the second derivative in the z direction. Here, kind of imagining these things, since we're only in 2 dimensions, we just imagine that we're in the xy plane, and so our z components are just going to be 0. We take the norm of that, we get the absolute value of the second derivative. The norm of the first derivative is just 1 plus f prime squared, square root of that. And so our expression for kappa in that case, our curvature, just is the absolute value of the second derivative divided by the square root of 1 plus the square of the first derivative. And so this kind of takes us through some of our important formulas for finding curvature. So we've got the special case whenever y is given as a function of x. We have the formula for kappa as so the curvature for an arbitrary parameterization for our curve. And then finally, what did we mean by kappa? Kappa was our norm of the derivative of the unit tangent vector with respect to arc length. So those 3 things kind of capture our notion for curvature. We've got an intuition for what it means, and so now we'll kind of pick this up and discuss it a little bit more in the next video, and I will see you guys then. Talk to you later.